I took a very old vise and turned it into the probably nicest working vise ever. And in this video you will see the full restoration, a new paint job and the 2 upgrades I did that made this possible. It's a Garant L with 125mm wide jaws, opens to about 23 centimeters and weighs 38 kilograms. If you wonder where this vise came from, my colleague Robin saved it together with a couple workbenches from a company that was sorting out old stuff. This vise was in use for probably 40 years and no longer needed or replaced. But the way it's built, it's pretty much indestructible. First thing I try to do is to get this rotating base moving again. It's kind of stuck and prevents me from getting out these bolts. This won't stay there. This won't work, so let's try removing the bolts that hold it together. I thought so. Wow, in there it looks brand new. Would be really handy to have a vise for this. It does move. The third one is still stuck, but I won't reuse them, so... Okay, it's moving, still very stiff, so let's try to take it apart and see what's going on. Oh, it's a tapered surface. Yeah, and probably just a lot of old grease that was causing the hard to turn nature. This lever then must be a cam that pulls on this bolt as I turn it. Yep, but it's very subtle, so a lot of force. And I should just be able to pull it out. Yep, there's the cam. Sweet. The screw seems to be fixed in place with a pin in this hole as it pivots around this hole when I wiggle on it. I'd say hit it harder. There you go. But the pin doesn't take the clamping force. That's done by the C-shaped disc. The pin keeps everything in place. That's already all the parts, so next comes cleaning them a lot and then trying to remove the paint. Some spots are so covered with sticky grease that I can take it off in layers with a knife. And I don't know why, but doing this feels incredibly rewarding when I'm just revealing the color again. It takes quite a while though, so after the first cast iron parts, I tackled the screw. The grease doesn't smell particularly nice, and looking at the consistency, good idea to get rid of it. The rest, however, will work a lot better at the lathe. Yes, I'm doing that with a rag and gloves, but super slow and my foot is on the brake the entire time. Not interesting, but rewarding when the shine finally comes through again. Next then is the handle shaft, which also had a thick layer of junk on it. And I don't know about you, but this feels a bit like scraping off a bit of history, or I helped the vise to shed its skin to a new life. Much better. Now the big parts. Also lots of really old grease and grime, layers of shavings from filing probably, and inside the hole here also a lot of just junk. Even some shavings that might still be there from manufacturing. But then more of the same. Scraping the thick layer with a knife, loosen the greasy stuff with a brass brush, and wiping it clean.
Quick workbench cleaning, and now we can move on.
So far so good with the rough cleaning. I got off all the old and sticky grease. Now I want to try removing the paint. Bought a paint stripper spray, and with that it should just flake off. Let's see what it does.
This spray needs to take effect for about 15 minutes and then...
There is definitely some flaking of the paint. I expected a bit more, but let's see. Oh yeah, it's definitely coming off. Let's use the paint scraper. Yeah, easy going now. Cool. It's definitely working, not as quick and magical as I was hoping, so I give it a second coat, do all the other parts as well, and also let it soak a bit longer than 15 minutes. That soaked for quite a bit longer, and you can see how it's flaking all over the place. It will probably still take a while to get it down to bare metal, but it's gotta be done.
Oh yeah, that took a while. Pretty much a full day with more spray, scraper and a wire brush. Really let me consider a sandblasting cabinet.
Now, having gone through all this trouble, I'm not just going to repaint it, reassemble it and call it good. I want to give it a very specific upgrade, an axial bearing. And fortunately, it arrived just in time. 2 of them. It goes in between the screw shaft and the front jaw and basically eliminates all the friction in between these two surfaces. Until now, this bearing job was done with just this metal disc and grease, and that's a lot more friction than a proper ball bearing. You can also see how much wear is in this part. And having virtually zero friction here means a lot less cranking force for reaching a certain clamping pressure, and especially a lot less force to release it again. However, this was not designed for this idea, and the bearing that fits doesn't exist, so I got the closest one and now need to machine both shaft and bearing to make this fit and work. Here we go. The first bearing race has an inner diameter of 35, which is the diameter it's made for, but the other one has 37. And the shaft itself has 37.3. So it is really close, and I just have to make the shaft a little bit smaller and the bearing race a little bit bigger. But let's see how much wall thickness there is behind the threads. Uh-oh. Dumb mistake. How do I get this out again? Well, snap gauge doesn't work here, so I quickly 3D printed this little guy here. Now I can read it with calipers, about 32. So the wall thickness behind the threads is about 2.65. And if I turn away about 0.5 millimeter, it will still be 2.4, which I'm pretty confident is enough.
But to put this in the chuck, the handle needs to go. Then I need to check the runout with the tailstock in place.
Could be better.
So to turn a new center, I switched to the 4-jaw chuck, dialed it in at the end, and took a couple light passes at a 30-degree angle. Then I chucked it at its bigger end, dialed it in again, and brought in the tailstock where now everything runs true.
With the axial bearing, I will no longer need this shoulder, so it can be turned away completely.
Very satisfying to see a shiny surface again. But pass by pass, it's going away.
All right, shoulder is gone. I'm down to 37.5 and now can start making full-length passes.
That's one of the best parts about turning. Me standing there, watching the machine work, seeing the surface finish with a smile on my face. But will the numbers agree with the smile?
I'm also seeing a very consistent diameter, plus minus 1/100 of a millimeter. That's very good.
The second pass leaves an even better, more consistent finish.
Interestingly, the surface is perfect everywhere except where the threads are. I wonder why that is. Size-wise, I'm at 36.95. I'll leave it like that for the bearing, and the final pass for the rest will be clearance.
And that's the final pass, finished with facing the shoulder.
Alright, that's the machining done on the shaft so far, and I think I could see the reason for the different cut qualities. This area here must be case hardened, which makes sense to make the threads more durable, and the chips came off in little flakes like these. And from here, they came off in long shavings. The bigger bearing race that needs clearance now clears everything nicely, good. And the smaller one I now need to machine to exact size to fit the little shoulder I left. Bearing races are hardened, so I need to grind this larger. Fortunately, I built an internal grinding spindle for the lathe in my last video. Let's put it to use.
But before grinding, I need a way to hold the bearing race, so let's machine a quick jig. It's basically just a bore with the exact diameter.
Nice. Perfect fit.
Then a relief bore so the grinding stone has some more space. And then with the milling spindle and a drill, 3 threaded holes to secure the bearing race with bolts. With that sorted, I could prepare the machine for grinding, which means covering all important surfaces and installing the grinding arbor, of course. Then I got the dresser installed and lined it up with the stone, put the dust collection over it and started dressing. Nice and sharp, ready to use. So plunging in until I see sparks, set some depth of cut and fireworks. Then it's just many passes. I went with about 12,000 RPM, 25 microns depth of cut and about 3 mm feed rate. Target diameter was 36.95, so once I got close, I dressed the wheel again since there is quite some wear visible. And the final passes I then made with 10 microns depth.
Let's take the measurement. I want to see 36.95. Spot on. Nice. There obviously are now very sharp edges and I could rotate the spindle and grind them precisely, but I could also just use the mini angle grinder and do this.
Got everything cleaned to flip around and chamfer the other side.
That really turned out nice, but does it fit? I'm looking for a almost tight slip fit and I shouldn't need to push it on. There will be a second bearing and both of them will be clamped together with a spring to the jaw, so I need to do the grinding again, this time fitting this diameter.
And this time, instead of the long grinding arbor, I'm trying this cheap and small grinding stone in the chuck. Apart from that, the dressing and grinding is the same. The stones are similar, so I didn't expect much difference.
Now, this one fits as well. A little looser, but that's what I wanted. Now, let's try it with the bearing bolt. Oh crap. Why didn't I see that coming? I don't think this is too big of an issue. I just need a different way of positioning the bearing bolts with a different cage, not the steel one that doesn't have an inner diameter. Sounds like a job for 3D printing.
So I took a top view photo of the bearing bolts with a ruler as size reference. Then I cropped the picture to the 10 cm marks and opened Onshape, the professional CAD software that runs in the cloud. There I drew a rectangle 10 cm long, imported the picture and scaled it to the rectangle. From there I measured the circle dimensions and used that to design a new spacer. That's it, and while printing I could destroy the old cage.
By the way, the use of CAD is a really powerful tool. I don't show it that often, but use it all the time in the background of my projects. And since Onshape runs on pretty much any device, you should really give it a try. You can even do so for free with my link in the description. And if you do so, you will help my channel as well. So thank you. Let's see how they fit. They snap in, are free to move, but can't fall out. That's good. That still works. And this now just clears the shaft. Good.
The second bearing gets the exact same treatment.
Finally, the 2 bearings are done. Next I need to make a bushing that goes in here, because once again, the bearing diameter and this don't match up.
At least this should be a very straightforward part, which I can turn out of the bearing race jig. Starting with the OD that needs to be quite a bit smaller than the stock, and turn it to a perfect 56 mm. Next, getting the big boy drill for removing all the center material and roughing the bore. The rest then with the boring bar. As expected, some straightforward turning, some inner chamfers, and the chamfer for the back edge while cutting off.
The sleeve has this very subtle shoulder, and in the upper part, where the moving part of the bearing is, it's a very tight slip fit, so it's still free to spin. And in the lower part, it gets a bit snug. And then in here, it should also be a snug fit, but not too tight, so I can just slide and tap it in. Okay, with this side taken care of, I can work on installing the second bearing, which, as you can see, isn't straightforward. Did I mention this wasn't designed for this axial bearing idea? Yeah, it really wasn't. But my idea to make this work anyways is to insert the bearing parts individually in this orientation, and I only have to file away a bit of material on top and bottom for clearance. That will be fun.
Yeah, that was fun. At least cast iron is easy to work with. And then I also remembered that I have power tools. The other side was just as much fun.
Yes, now they just fit through. Can orient them and stick the shaft through. All right, bearings are in, and if I press against it, it spins super easily. Now those bearings need to be pre-tensioned against each other and to the jaw, so it's not loose like this, but always like this. And finding a spring for that was also a challenge. What I ended up with was one of these wavy spring washers that for once I don't have to modify in any way. But to apply the tension, I need some kind of a clamping sleeve that pushes the spring against the bearing and then can be fixed to the shaft. Perfect job for this little offcut of round bar.
Unfortunately, most of this material will be chips, but at least it's quick with this chonky boy. Rest then of course with the boring bar until it's a perfect slip fit. Then I brought the chuck into a known position with the digital angle gauge for some threaded holes that start out with the spot drill. I did 3 in total and could use the chuck jaws for repeatable positioning. Should really upgrade this with an indexing plate though. Then the same for drilling, chamfering and threading, where the spindle worked as a guide. Finally a decorative chamfer, and this part is done.
Now to tension this spring, I made this block of wood with a hole, and with another board clamped to this end, I can squeeze the spring together and then tighten the set screws. Clamps are removed, it's still nicely free spinning, but now pretty solid, and I can now push and pull on it. That's it with the axial bearing upgrade. Quite a bit more involved than I hoped, but it's done, and I can move to the second upgrade I want to make, a new and better handle. For my lathe chuck, I already made this handle that has a spinning knob and is expandable. And I want those two features on the Vise. So let's build one.
Got the design, drawings and material. Let's start with the handle shaft. It's long, so a center for the tailstock. There needs to be a groove along the length, which is another job for the milling spindle. I had to play a bit with the feeds and speeds until the cutter was happy with the setup. But then the chips were flying.
So far so good, the slot is at depth, but it should be 8 mm wide, not 6. So I now adjust the cutter up and down to make a finishing pass on top and bottom.
Setting this up with calipers and send it.
The surface finish is fantastic. But power feed would be useful.
I ended up making 2 finishing passes on top and bottom to get the dimensions correct.
Definitely overkill, I don't need this precision here, but this is an 8 mm gauge block and it fits nicely all the way. Just a little bit of wiggle, and here I have a gauge block stack with 8.04, and that's the size I got. Pretty good.
The second feature on this part are some rounded grooves, for which I switched to a ball nose end mill, simply plunging in while the lathe is spinning slow. And doing it 3 times. That's it, so I cut it off and tried it out.
The purpose of this groove is to, together with a pin, keep the orientation of the handle, so the spinning knob is always oriented the same. And for the vise handle, I want to try using the shank of a broken carbide end mill, which should be the most wear-resistant material I have. Got the bit in the chuck, a diamond disc in my spindle, and dust collection set up. Let's see if it works. Seems to work. I'm actually using power feet, super slow though. But this looks promising. And it sucked it up, of course. Fortunately, it's heavy and stopped right there. There it is. And a super clean, burr-free cut. Next, I need the handle shaft back.
First of all, making the rest shiny again. Then drilling and reaming an 8mm hole to a certain depth for the right amount of stick out. Everything looked promising until...
a little bit of slop. This slop is expected, but this not. Shit. For some reason, I didn't measure the actual hole diameter and just went with the original handle diameter of 16mm. But the hole is more like just over 17mm. And this has a ton of slop. But everything else with the carbide pin works fine, so I did the reasonable thing and just remade the whole handle shaft.
And this time, I checked the size. It also allowed me to use a better strategy for the rounded grooves, so they don't intersect with the other groove and cut away material where I need it.
And now, this is the fit. Much better. Very little slop and super easy to slide.
Next, I oriented the hole vertically to drill and ream a cross hole for the spring-loaded ball detents.
Unfortunately, my reamer seems to cut undersized and this ball just doesn't fit. But I can try a machinist trick that I've seen a couple times already, which is a couple layers of cloth in between the reamer. And that should enlarge the hole just a little bit. And... oh, fits. Very cool.
Lastly, threads and assembly.
2 steel bolts, set screws and spring donors. And there we go. Nice, clicky, positive stops. Next come the spinning handles, which I'm gonna turn from some bronze.
Very simple parts. A ream through hole, then countermill to fit a bolt head, a very simple shape, knurling, chamfering, and done.
That was easy, but not so much the parts that will connect them to the handle because of the large cross hole, but I have an idea.
That requires switching to the central 4-jaw chuck and clamping the part like this. And now, turn milling the hole. It seems to just work. I let the power feed do its thing and took care of removing the chips. And once at depth of almost 20mm, I slowly enlarged the hole by moving the cutter outwards and creating a lot of needles. I didn't know what to expect, but it just worked without any chatter.
Haha, nice. What a beautiful fit. Such a versatile tool. This is what pain looks like. With the hole in place, I can turn the rest and base the dimensions off of that.
So after getting rid of the axis, I could use the handle for measuring and turn the outer dimensions, followed by some threads. Flipped around and cut to length, it's more threads, and then turning down until it's a perfect fit for the spinning knob. The other dimension that needs to be right is the length, so when the knob is in place and the bolt is tight, it's still free spinning with minimal play.
Alright, with those made, I should be done with the upgrade parts and can continue on all the other parts to get them ready for a test assembly.
It's actually not much. I stoned the flat surfaces in reach, and the rest was Scotch-Brite on all other machine surfaces.
So, get everything clean and dry, ready for a dry assembly.
And back together it goes.
Ah, that is smooth. And No backlash. That will be great. And this was something I was really looking forward to. Since the handle is now balanced and pretty heavy, it acts kind of like a flywheel. And it's great. And remember, nothing is lubricated at the moment, so this should even get better. Now it's ready for painting, then lubricating, and then actual clamping. There's a problem. I of course did some clamp testing, but having done it without grease must have caused this bearing race to seize itself in this new bushing. This probably happened because when you're cranking, you're not only applying force axially, you're also applying it radially, as you can see here. Well, and without grease, I hoped it wouldn't happen, but it did, so let's look at the damage. Good catch. Yeah, there was some gulling going on, both on the bearing race and the bushing. Now what?
Well, first getting the bushing out as well.
Okay, got it back. Maybe there's a simple solution. The fundamental issue was that there wasn't really a component designed to take the radial forces from cranking, which caused the bearing race to rub inside the bushing and eventually start gulling. And true, the axial bearing is not designed to take radial loads. As you can see, it's wiggling around. Except when it's under high compression, then thanks to the ball grooves, it should be able to handle reasonable radial forces. Well, and in my Vise assembly, it's always under compression, either from the spring washer or the clamping pressure itself. And when there is a lot of pressure, you can see the wiggling gets a lot less. So maybe I just didn't leave enough room here for this bearing race to wiggle enough and not contact the bushing.
And that means the fix could be as simple as putting the bushing back in the lathe and removing just a bit more material.
Much better, much better. Now it's working and clamping again. Amazing how such a tiny little clearance, or rather missing clearance, can cause such a big issue.
So with that sorted, I could finally prepare the parts for painting, which is probably the most important step to achieve a good result. So I got everything cleaned with brake cleaner and carefully taped all machine surfaces.
For the finish, I'm gonna use the same light blue hammered finish that I already used on my homemade edge clamps and the oscillating belt sander. But this time spraying it on actual metal, not wood.
Spraying this then is really quite simple, and I love the look. I applied 2 coats spread over 2 days. While the paint was drying, I took care of one other part. The cover plate in the front needed to get larger to fit around the new bushing.
The paint's dry and the parts look fantastic. Now comes the best part, removing the tape again. Everything on this paint job turned out fantastic and we can move on to the final assembly.
Now the bearings also get a final cleaning and then lots of grease. For the spinning handles, I also printed some soft washers to dampen the impact when extending the handle. I wasn't quite sure about the lubrication of the vase and put on some whey oil from the lathe.
But what do you think? Oil, grease, graphite, or just dry? Let me know. And it's done. Let's clamp something. I'd say that's tight. I don't have a probe to measure the actual force, but come on. I'm certain this is enough. And now what makes this vise special with the axial bearings, unclamping this is as simple as that. And the other advantage is the backlash, or rather no backlash, because that's all there is. This will serve me well, but one question remains: where to put it in my shop?